Hi, welcome to the presentation of robotic manipulators in agriculture, a brief review. The demand for manipulators in the agriculture industry has never been greater. This paper discusses literature within the last decade that covers motion control and planning, gripper harvesting, gripper planning, gripper structure, and materials that are utilized. This paper later discusses future work for manipulators to administer to the agriculture industry. So, to begin with, we have the introduction for this paper. In 2014, the UK government identified robotics and autonomous systems as one of the 8 great technologies for the UK's growth. We can apply this to the agricultural domain. We need to do this due to a 30% shortage in fruit pickers and with an increased demand due to the pandemic in 2020. Moreover, manual labourers often experience musculoskeletal problems when working on agricultural tasks. So, the solution is to develop and deploy manipulators into the agri-domain. So, we began with motion control. Unfortunately, most of the research within motion control has not been applied to agri-robotics. Agri-robotics is subject to unstructured configurations with complex dynamic environments, which are difficult to control with a simple PID controller. Current applications within motion control use neural networks to approximate torques and velocities when handling and manipulating fragile agricultural harvests. Neural networks can be used as control mechanisms to approximate either the robot plant or the control mechanism within the closed-loop feedback control to accommodate for the complex dynamics. Other methods aim to improve PID control to be deployed for use in the agri-domain, using techniques like fuzzy logic and adaptive hybrid systems. These are explored more in depth within the paper, as you can see in Figure 1, is one of the systems we have reviewed. Moving on to motion planning, we look at learning from demonstration, or LFD. LFD ensures manipulators can plan the correct path to take when moving around in the workspace. LFD can be simplified by just averaging the recorded and finalized trajectories, followed by Gaussian processes. It is able to detect constraints and thus can learn abstract concepts which dynamic movement primitives cannot. Combining LFD with constraint-based task specification using probabilistic principles component analysis enables the specification of a set of reactive behaviors taking into account sensor inputs, making the system robust against uncertain environments, which is essential for the agri-domain. Integrating simulation with robotic LFD improves the accuracy and task performance compared to state-of-the-art models available. It minimizes the time requirement in the learning stage and substitutes learning with physical systems. Shown in Figure 2 is one of the systems we review. In agri-robotics, the grasp planning problem is often to define a pose where a target crop can be securely grasped on the segmented image or point cloud of the target. The methodologies used for gripper planning in agri-robotics include the fitting of geometric primitives to the segmented fruit in an image or point cloud, and selecting a grasp pose based on the primitive orientation. Figure 4 shows a number of poses on a super-ellipsoid primitive, fit to a sweet pepper from one of the papers we review. The use of algorithms such as particle swarm optimization based on the geometry of the target object to choose an ideal grasp, the application of machine learning trained on databases of grasp poses, looking up features of the segmented point cloud to retrieve a prototype grasp pose from a database. Some of the tasks in gripper planning include the decomposition of the entire model into submotions, transitioning from offline pre-computation to online computation, optimal point selection for efficient grasping, and accurately grasping the target while avoiding collisions with nearby objects. These are explored within the paper more. Moving on to gripper design, compliant grasping is dependent upon both the structure and material used within the gripper. Cutter designs are common for crop harvesting to detach the fruit from the stalk. Some designs use a clamping mechanism as shown in Figure 5, which hold the fruit. This design is a universal design implemented to clamp many different fruits. Whilst the idea is nice, it fails to handle many crops, and hence a fixed set of parameters for such a design is insufficient for all crops. Crop-specific designs are preferred. For instance, for tomato harvesting, a cutter design and a suction cup would be better. Rigid materials struggle and don't allow for flexible or dexterous grasps, which are critical for applications such as fruit picking. Hence, the latest soft materials have been reviewed. More information on all of these soft materials can be shown in the paper. They do show potential with grasping, but have yet to demonstrate in-field harvesting. So, to conclude, the review covers an investigation into manipulators for the agri-domain, discussing motion control, motion planning, gripper harvesting, gripper planning, and gripper structure. Thank you for listening.